Thank you to the organizers. I've really enjoyed being here these 2 weeks. Some really excellent lectures. I hope I can get close to what some of the others have done. And thank you all for coming. I see we have almost a full audience still. I was doing speech for about a quarter of a century, and now I'm generalizing to more general machine learning. So at my new employer, we'll be doing model-based machine learning, mostly with small data sets, so it pays to be Bayesian. But I'm not going to talk about that now. I'm going to talk about plumbing. So differentiation is as important to machine learning as water is to all of you. So many of you, when you need water, you can just open the tap and forget about where it comes from. But some of you might be interested in a career in plumbing, and then it might help to know a little bit more about automatic differentiation. And if things go wrong, of course, when there's a drought, it helps to understand why there's no more water in the tap. So, as you know, most of the machine learning toolkits these days have differentiation built in. Most of those are implement what's called reverse mode automatic differentiation. So I'll summarize that in the end, but I'm going to spend more time on the forward mode, which has some interesting possibilities in some other applications in machine learning. So we'll start with the usual kind of stuff. Where do we find derivatives? Why? And what is automatic differentiation? And so on. So derivatives of complicated multivariate functions are an essential part of modern machine learning. The first application that comes to mind when you're optimizing things, when you're training a neural net, or when you are optimizing the variational parameters of a probabilistic model, you need to go down the gradient and you need to find the gradient. So if it's a complicated network of interacting functions, a function composition, that's quite a hard problem to calculate the derivatives. And if you're doing things in a more Bayesian way, you might be doing sampling, and some of the sampling algorithms in continuous spaces, they're driven by derivatives, for example, Hamiltonian Monte Carlo. And then every now and then you need derivatives in other places. Last week we had a lecture on GANs, and one of the ways to make the GANs behave nicely is to have a gradient-based regularizer. And there are many other examples. So why this tutorial? I've already answered this question. So if you want to create new tools, architectures, new inference algorithms, new regularizers, then a basic understanding of the principles of automatic differentiation could be very useful to you. So I can just add why I'm giving this talk. I was interested in automatic differentiation before these tools in TensorFlow and similar were available. So I just found out for myself how to do it, and I did it. And so I've never contributed to any of these tools, but I got my experience from implementing it myself. So what is automatic differentiation? It's important to realize that it's different from symbolic differentiation. It's also different from numeric differentiation. So let's try to zoom in. So who can give me the derivative of the sine function? Okay, it's trivial. But we're not going to cut open your heads and wire you up to a GPU. So it doesn't really help to know that the derivative of the sine function is the cosine. For machine learning, we just need to know the value at some specific value of the arguments. So you get some really nice tools that will do symbolic math for you. For example, Mathematica has such a tool. But Mathematica probably can give you the derivatives that are going on inside a big neural net, but the answer will fill pages and pages, and it's not in a useful form. It's not directly applicable to machine learning. So numerical differentiation, sometimes called finite differences. I'm sure most of you will be familiar with these little formulas. So you evaluate the function in the place you're interested in the function, and then you move a little bit with a small delta, and you just get the ratio over here. So one of the problems is you have to tune this delta. If the delta is too big, you're essentially smoothing and distorting your function. You're getting the derivative of the wrong function. If you make delta small, then after a while, X doesn't notice anymore that you're adding delta to it, and you get numerical effects, and it also becomes inaccurate. So depending on your function, you might have to tune delta, and you're never going to get it very accurate. So you'll see I have two variants. The one is symmetric, and the other one is not. So can I have a vote? So which of the blue, well, who says the blue one is faster? Nobody knows. Okay, so if you're going to evaluate your function at x anyway, which is what you'll usually be doing, the blue one is faster. Because then you just need to do one extra evaluation at x plus delta. So who says the red one, which is slightly slower, is more accurate? Okay, good. So it's more accurate because it cancels an extra term in the Taylor series expansion. So if you're going to do this, use the red one, not the blue one. But hopefully, after you know what automatic differentiation can do for you, you will only rarely have to resort to doing your derivatives in this way. So the biggest problem with this method is that it's intractably slow for large gradients. So if you're sending this little delta into your neural net from the input side, you're going to have to do this once for every different parameter in the neural net, and as you know, that can be millions or or many millions. So it's completely impractical for optimization purposes. So automatic differentiation, this might look like magic to the uninitiated. You send a special argument into your function. This E is, or this epsilon here is not a real number. It's something special. But anyway, in principle, you can send one argument into your function, and on the other side, you will get an answer with two components, and you've got the function value, and you can go and harvest the derivative almost for free, it seems. So I'll explain that later, of course, but it does exactly what we need for machine learning. It evaluates the derivatives at the place you're interested in. It does this to machine precision, typically, and it can often be as fast as hand-optimized code. So there are two main flavors of automatic differentiation, forward mode and reverse mode. And I can just quickly summarize some of the properties of these two. So forward mode is relatively easy to code using operator overloading, and I'll show you a really nice trick called the complex step trick, which requires almost no coding effort. It's mathematically cute, but it's too slow for gradients. It has the same problem as the finite differences. If you want a gradient, you're going to have to do this for every single parameter in your thing you want to train, and that's going to be too slow. But I'm going to show you two useful things that you can nevertheless do with it. Just so you can verify the correctness of derivatives that you get out of your favorite toolbox, or maybe derivatives that you implemented yourself. And then we're going to talk about Hessian vector products too. So the reverse mode is harder to code, but the good news is it's there for you to use in those toolkits. So it can do either on-the-fly calculation, or it can generate code to do the derivatives for you. And the gradient is fast and therefore good for the typical kind of optimization problem. So let us zoom in and explain this difference between the forward and reverse modes. So this is a typical machine learning problem. It might be a two-layer feed-forward neural net, but it could also be some component inside of your variational autoencoder or somewhere in your GAN. And of course, you can have more than 2 layers. I've only got 2 layers here to make the notation easier. So what's going on here is function composition. So the functions I have here, f and g, they map both their input and the parameters to their output. And then finally, the last thing you will typically be doing is you'll feed the output of the net into some objective function, a scalar valued objective function, which might be cross entropy if you're doing classification, or it might be the elbow if you're doing variational Bayes. So we want to learn the parameters in this slide, theta and phi, by going down the gradients of those parameters. So those are the partial derivatives with respect to the output C of those parameters. So let's just explicitly define the gradient. So let's zoom in on the gradient for theta. The gradient for phi is similar, but the gradient for theta will illustrate what we need to know. So first of all, if it's a neural net, theta will be the whole weight matrix and the biases. You just flatten the matrix and put it in a vector and add the biases. If you've got a more complicated architecture where you've got some parameters like the means and log variances of Gaussians, you just stack them all. It's one vector of parameters. So when you're talking about optimization, it's nice to see the parameters as just one big vector. So we're following the path from the output, the objective function C, all the way back through the composition to the parameter we're interested in learning. So one way to interpret the gradient is if we multiply the gradient, this red guy here, with some small perturbations in the parameters, that inner product there will give us the small change in the output. Another interpretation of the gradient is the direction of the gradient is the steepest descent, and that's a kind of semi-sensible direction of finding the minimum. There's a lot more to say about whether it's a good idea to follow the gradient or some other direction, but this is not a talk about optimization. So when you're doing function composition and you need to calculate the gradient of such a function composition, there's this chain rule, which is really just matrix multiplication. So every function has associated this Jacobian matrix. So the Jacobian matrix, remember, the top function there, f, has m inputs and it has n outputs in general. So the first layer of a neural net, m would be the number of components of your input, and n would be the number of hidden units. So in general, we've got these functions that map m to n. So if you calculate all the possibilities for first-order partial derivatives, that is a matrix. That matrix is called the Jacobian matrix. So every function in this composition has a Jacobian. So the last one is special because the output, the cost function, is scalar. So that becomes a row vector. So to get the complete gradient in this function composition, we're just multiplying Jacobians. So now we get to the difference between forward mode and reverse mode. So you can group the matrix multiplications in two ways in this simple case. If you have many layers, there are many ways to group them, but forward mode would start from the left and keep multiplying. Reverse mode would start from the other side and keep multiplying. So who would vote that forward mode is faster? Nobody thinks so. Who thinks reverse? I've already told you. So if you start from the left-hand side, you're doing a matrix multiplication, which is expensive, and then finally you're multiplying it with a vector. If you're coming from the other side, you're doing a vector matrix multiplication and then another vector matrix multiplication. It has to be faster. So not all calculations with derivatives are like this, but if you've got a scalar objective function, then you always have the last Jacobian is always going to be a vector, and then it's always going to be faster starting from the outside function in the function composition. So just a little example. You can imagine building a two-layer, well, a little neural net to classify MNIST digits for you, where there's one layer of hidden units and two matrix multiplications. So the output will have just 10 units, which will be the log probabilities for each of the digits. Yes, I've got 1,000 hidden units here, which is maybe a little bit too much, but okay. And we've reduced the, I think it was 28 by 28 input to just 100 dimensions using PCA. If you just evaluate the function value, that's for one data point, one digit, then the cost is going to be roughly 10 to the 5. If you do reverse mode automatic differentiation, the fast way to do it, then the cost is already going to be proportional to 10 to the 8. If you multiply the Jacobians from the other side, it's already 10 times slower, but in the way that forward mode AD is usually implemented, it would be even slower because it's going to be like if the cost of evaluating the function m times for each of the weights in the initial big matrix. So it's going to be then 100 times slower than the reverse one. And if your network is bigger, it's going to be even worse than that. So let us now look in more detail at the forward mode. So to understand forward mode, let's just do a quick revision of complex arithmetic. So in complex arithmetic, we say define the special abstract number which we can call I. I is equal to the square root of -1. And if we square it, indeed, we get -1. There's no real number that can do that, but we say let's just define that nevertheless. And if you allow that I inside of your number system, things work out very nicely, as you all know. So we can represent a complex number as having two components, the real and the imaginary number, imaginary component. And addition is straightforward. You just add the components like any other two-component vector. The multiplication, you get these cross terms, and because of the square root of I being minus 1, we get this in the multiplication. In the real part, you get this minus BD term, which I've highlighted here, which might be a little bit unexpected. So dual numbers are very similar to complex numbers. It's also has two components, but now instead of an I, we're using an epsilon. And this epsilon, you can imagine it as being a really, really small number, an infinitesimally small number. And it's not quite 0, but let's define mathematically if we square it. If you square a small number, it gets a lot smaller. Let's just say it becomes identically 0. This is how this number system works. So the addition, we're just adding components. The multiplication, this cross term that we had before, this BD, doesn't happen because E squared is 0. And that's going to be very useful for our differentiation purposes. So, to show how the dual number makes differentiation happen, we look at the function at some real argument a, and then we do a Taylor series expansion about a. So the difference between a and the argument that we're actually sending into the function is epsilon b. So b is a real number, epsilon is this really small number. And then the Taylor series is an infinite expansion with all of the derivatives of the function. But because e squared is 0, e to the third is also 0. So you're truncating the Taylor series after the first term. All the rest of the terms fall out. So in the end, the only extra term that remains is the first derivative. And since the function is since this number is represented in two components, just like a complex number, after we've done this, we've sent this dual number argument into our function. At the output side, we can then harvest the real part, which is the function at a, and also a multiple of the derivative. So you can set b to 1, or if b is not 1, you can divide by b, and you can retrieve your derivative. So, okay. Just to convince you with an argument somewhat simpler than a Taylor series, let's just do this for a very, very simple function. You just square the argument, and epsilon squared disappears, and you've got the function value a squared and the derivative 2a, and things work out. So for our applications, we're almost always going to be playing with multivariate functions that map m-dimensional vectors to n-dimensional ones. So in this case, things generalize in a straightforward way. So if we send a dual number argument into the function, we'll get the function value in the real part of the answer, and we'll get the Jacobian. Remember, the Jacobian is this matrix of first order partial derivatives times this vector b that we've sent in. So both a and b are real valued m-dimensional vectors, and we're just putting b into the infinitesimal part of the argument that we're sending in. So if you really want the whole Jacobian, which you wouldn't want in practical applications, but if you want the Jacobian to look at it, to compare it to something else, maybe in some contractive autoencoder, you want a regularizer that needs to compute the determinant of the Jacobian matrix. That's one way to get the Jacobian. So you send one hot vectors into B, but you're going to have to do that for each of the columns of the Jacobian. So even if n is 1, the dimension of the output of your function is 1, then the Jacobian is going to be a row vector, or if you transpose that into a column vector, that's the gradient. But you're going to have to do it m times 1 for every component of the input. So this is why forward mode is not your weapon of choice for optimization problems. So how do we do it in practice? This epsilon is an abstract number. How do we do it in practice? So the exact way to do it would be via operator overloading. And in a language that allows operator overloading, for example, Julia, this is really fun to do. I've done that. So you declare a new numeric data type, and then you need to re-implement all of the operators, plus and multiply and divide and so on. And then if you want things to be fast, then you need to re-implement all of the linear algebra stuff that you're going to be using in your code. And you're going to have to, for each of those things, matrix multiplication, solution of linear equations, Koleski decompositions, all those things you're going to have to re-implement for complex numbers. And if you want things to be fast, you have to call down into your favorite implementation of BLAS and LAPACK and so on. And of course, all the other functions that you might need, you need to implement them too. So I've played around with that. If the language nicely allows operators, then it's fun to do, but it's a lot of work. But there's a very accurate approximation which you can do with almost no coding effort. You can't always do it, but let me explain. So we're approximating this epsilon, this infinitesimal epsilon, with an imaginary number. So 10 to the 20 times I. 10 to the minus 20 times I. So epsilon has to be really small. We're making it really small. And we're keeping it separate from the real component by leaving it there in the imaginary component. So this tilde epsilon is a pure imaginary number. And if we square it, it becomes a lot smaller. And we can say for practical purposes, for numerical purposes, it's just 0, and we don't need to worry about it. So that's how we're going to practically implement this thing. So if your function is equipped to handle complex arithmetic, then you can just send this approximation to a dual number which you've manufactured. You can send that into the function. If you take the real part of the output, that's just the function value again. And if you want the derivative, you take the imaginary part and you just multiply by 10 to the 20, and you've got your derivative. So next time you're sitting in front of Python, just try that. It's a nice trick. So just like the dual numbers, it works for multivariate functions as well. And you just recover the product of the Jacobian with some vector by taking the imaginary part and rescaling it. So the complex step trick is very useful in practice. I use it all the time. But there are a few things to watch out for. So some languages might not allow complex numbers at all, or even in your favorite language, the function that you're interested in might not, that function might not allow complex arguments. Also, I've had some experience in Julia doing this, so and in MATLAB. In MATLAB and Julia, I did this, and in MATLAB it would work, and in Julia it would not work. And then I would raise an issue, and overnight the people who work on Julia would fix it. Their day in America, my night, they would fix it, and and the next day, automatic differentiation using complex step would work in Julia. So that was a nice experience. So yeah, there are different ways to implement functions, and I had to explain to them why I was doing this, and yeah, that was nice to work with them on that. So other things, you can't use it to differentiate operations which already use complex arithmetic. So if you're doing FFTs and the complex numbers in the FFTs are important, then you need to watch out. It's probably not going to work out like you think it should. You can't apply it twice to get second-order derivatives, because once you've done it, you've got complex numbers, and then it's not going to work anymore. And then you have to make sure if you're transposing matrices as part of your calculation, which of course you do almost everywhere, then make sure the language doesn't just by default take the complex conjugate. It has to be a pure transpose, not the complex conjugate. So in MATLAB, for example, if you put a prime after the matrix, that means the complex conjugate. So if you're doing real calculations, that doesn't matter. But if you're doing this, you have to add a star prime to tell it this is the one you mean. And then if you're doing square roots or Cholesky decompositions and other functions that expect positive or positive definite arguments, you need some extra care. There's more to be said of how to do differentiation through those things. I don't know if Ian is here. Ian can differentiate through the Cholesky transform. He's got a publication on that. You can use things like that. Okay, so this is quite a complex slide, but we've got lots of time to explain. So I have not seen this published. I use this all the time. It's kind of obvious, but it took me a while to think of it. Nevertheless, after you've seen that, it's obvious. Before you've seen it, maybe not. So, if you have some platform that provides a derivative, let's say reverse mode automatic differentiation, and you don't trust it, so I've put a little question mark at the Jacobian there, which means that Jacobian might not be the true Jacobian. We want to test it. So it could be somebody else's code, it could be TensorFlow code, or if you're implementing reverse mode differentiation yourself, it might be your code. You want to know, is the derivative correct? Then you can test, you can compare the results of the version you want to test against a forward mode calculation. So the blue box on top represents the derivative calculation that is already implemented that you want to test. So for a function from an m-dimensional to an n-dimensional vector, the derivative is just the Jacobian. And the typical backpropagation reverse mode differentiation operation that your existing tool will be doing for you is to multiply the Jacobian transpose with some vector b. So this guy over here, that operation is really the one we want to be testing. So then we send the same argument into the same function that we're interested in, but we're using a dual number argument to send in there. In practice, you can usually implement it with a complex step trick. And then that Q, the infinitesimal component of the output, or in practice the imaginary component, from that you can then harvest the Jacobian multiplied from the other side. So you'll notice the reverse mode one multiplies the Jacobian transpose. That's the same as multiplying the Jacobian from the left. And the forward mode does multiplication of the Jacobian from the right. So the results of these two operations, call them P and Q. And then You just need to supply the other vector from the other side, and the test that you're going to be doing is the top one here. So, of course, we're working with real numbers. It's not going to be exactly equal, but typically I find 10 to the minus 12, that's the maximum absolute error in that kind of calculation. So if the top equality is satisfied, that implies that the bottom equality is also satisfied. So you haven't shown that the Jacobian with the question mark is equal to the other Jacobian. You've just shown that those bilinear forms there involving the Jacobian are equal. So if you draw a number of random vectors A and B, and you do this a few times, then you can say, well, okay, I'm starting to trust the implementation, and so it's a stochastic verification of derivative. Of course, also, if your function is nonlinear, the Jacobian is going to be different at every function value, so you send in a few random different values of x. If you suspect that at some region of x, the derivative implementation might be suspect, you can test it there. So the x that you send in, you can make it random or you can control it. So if you remember nothing of my talk, remember this. If you don't trust the derivatives, you can go and test them. And I've mentioned that there might be some problems. Complex arithmetic might not always be available. Then you can fall back on the finite differences. But it's harder to tell whether the error that you're seeing is because of the inaccuracy of the finite difference or because of some error in the implementation that you're testing. But you can usually get around that with making your problem smaller. So this technique over here, you can do it for a large neural net. So because it's fast. So you can hook up everything and test everything together with this technique. And if you're sitting there, you're doing something new, the optimizer isn't doing anything useful, you ask what's wrong. Obviously, if the derivatives, the gradients are wrong, that's going to be a good explanation for why your optimizer doesn't work. So it's really nice to be able to test your derivatives. So let's get to another application of forward mode differentiation. So I said the complex step trick is no good for second order derivatives, but we're going to show you there's one special case here where we're going to get second order derivatives of a special form out of the forward mode differentiation nevertheless. So we're talking about the Hessian matrix. So the Hessian matrix is a word you would use in the context of a function that maps a vector to a scalar. And then you're taking the derivatives of the output with respect to first one of the components of the input and then another one. So you're doing two differentiation steps, one after the other. And if you have an m-dimensional input, there are going to be m squared possibilities. So all those partial derivatives we're collecting in a matrix. That's the Hessian matrix. So for a well-behaved function, the Hessian matrix should be symmetric. You can construct some pathological functions where that's not going to be the case. We're not going to worry about those. So some applications in machine learning and probability calculations for Hessians. So Newton-Raphson, or sometimes just Newton optimization, you would multiply the inverse Hessian with the gradient, and that's a really good direction in which to minimize. if your function is quadratic that you're trying to minimize, this Newton step will land you at the optimum in a single step. So if the function is not quadratic, you might not want to go all the way along the Newton direction, and then you get algorithms that do line searches or more complex algorithms that are called trust region algorithms. So trust region algorithms are really powerful. They can minimize non-convex optimization functions. They can even escape really nicely from saddle points and maxima, and they just go downhill. But the problem with those algorithms are that this calculation, this linear equation which you have to solve involving the Hessian, if the Hessian is large, you just can't do it exactly. So you get a class of optimizers called truncated Newton optimizers, which solve this linear equation approximately using, for example, conjugate gradients. And the conjugate gradient is driven by Hessian vector product. So you've got some test vector that you keep on multiplying with Hessian, and that will give you, with, if you're lucky, an affordable number of Hessian vector products will get you somewhere near this Newton direction. So you get a whole class of optimizers that do that, and for some problems that might be a nice thing to do. So these days, machine learning typically doesn't do that. You've got these stochastic gradient optimizers which don't even try to get the Newton direction. They just go down the gradient, and I can't really explain why that works, but if you've got this long narrow valley with a slight slope at the bottom of the valley and your minimum is over there, and you're sitting here on somewhere along the side of the valley, downward is there. That's not a good direction to find the minimum there. And if you're going down the minimum, you're gonna just oscillate in the long narrow valley, and that's why the Newton direction is much better, but that's not what modern machine learning does. So I'll leave that to somebody who understands that better to explain why it works nevertheless. So let's leave optimization behind for a moment, and let's say you're doing Bayesian inference and you want to do some evidence calculation. There's the Laplace approximation. So the Laplace approximation is kind of old, and it's often ignored these days. But if you've got if you're interested in the posterior or the evidence involving one variable or maybe 5 or 10, then the Laplace approximation is often quite easy to do and easy to understand, and it might be a nice thing to do. So anyway, the Laplace approximation, the main computational thing that you need to do is you need to calculate the determinant of the Hessian matrix. Then this was mentioned yesterday by Neil. He was talking about probabilistic models that want to calculate the probability density for you, but the normalization constant is missing. It's there. The idea is that you can normalize the probability density, but you just can't calculate the normalization constant. So there's a criterion published by Hiverinen called score matching, which if you optimize that thing, you don't need the normalization constant, and then you can do, it's not maximum likelihood, but it's very similar to maximum likelihood. You can train a non-normalizable probabilistic model by going down the gradient of that optimization criterion. So To do that, the hard part is you need to calculate the trace of the Hessian matrix. So that's one of the reasons why people aren't really using it, because of the trace of the Hessian matrix. If it's a multivariate Gaussian, the Hessian is just the covariance and the precision matrix. The precision matrix, it's right there looking at you. So for multivariate Gaussians, it's not hard. But for more general functions, this is a tough calculation, and that's probably why people are not using score matching more widely. So some challenges. Your favorite machine learning toolkit doesn't necessarily supply Hessians. If you're going to do it by hand, if you've got a complex function composition, even not that complex, maybe you're just composing two. Don't know if anybody's ever tried to take a Gaussian mixture model and derive the Hessians of just the parameters of Gaussian. You don't want to do it. So you'll fill pages and hand coding, you're just not going to get it right the first time, or maybe the fifth time it still won't be right. You don't want to do it. So the other thing is, for m variables, the Hessian has m squared components, and you'll never be able to calculate all of them, let alone store them inside your computer. If you're using that Hessian to do stuff, you just can't. For example, if you want to exactly solve this linear equation, which I've mentioned before, the cost is m to the third. You're not going to even think of doing it. So, solutions. So, if we can efficiently compute this Hessian vector product, so an arbitrary vector of the same size as the input, you're multiplying this with a Hessian matrix. We're not going to do this explicitly. I'm going to show you a way of doing it implicitly and with low computational cost. If we can do that, then we can solve some of these challenges, some approximately. So if m is small, then not a typical machine learning, deep learning type of thing, but if you've got a small probabilistic model and you want to be Bayesian, then, or even if you're optimizing the parameters of model and you want to optimize them exactly with a high precision optimization, then you can use this trust region method with using Newton directions. So then you might want the full Hessian matrix, and Laplace approximation in low dimensions. You can recover the full Hessian matrix with the Hessian vector product. So you just send one hot vectors into Y for every column, and you've got your Hessian matrix, and you can do whatever you want with it. So it's the speed of doing that is for a small problem. You can manage that speed. It's not going to kill. The computation is going to be fast enough, but you've avoided the error-prone hand coding of second-order derivatives. So for large M, we can use a relatively small number of Hessian vector products to, as I've mentioned before, conjugate gradients can approximately solve this Newton direction for you. If you need it, then you can even do a truncated eigenanalysis of the Hessian for you. So that means you find the few biggest eigenvectors and eigenvalues and the associated eigenvectors. So there's this Langsos algorithm. I know in MATLAB it's called eigs. You can just send the Hessian vector products into eigs, and you can then do an eigenanalysis of the Hessian. So you can also do things with the trace. So last week Shakir mentioned this trick already. So you sample some random vector. So the random vector has to be independent and scaled in such a way so that this outer product of that vector with itself is the identity matrix. And then if you do that a few times, then then that quadratic form over there will be an approximation to the trace, unbiased, because the trace is equal to the expected value. So when I was playing with restricted Boltzmann machines, there's this contrastive divergence method to optimize the parameters, but you're never really sure where you are, how far have you optimized. So then you can apply Hivarinen score matching criterion to tell you how well you're doing, and I use this trace trick using Hessian vector products to get an approximate evaluation of that score at essentially no coding cost and quite fast enough. So there are some places where this might be useful. So how do we do it? I've tried to convince you that sometimes it's useful. How do we do it? So this is sometimes called the Perlmutter trick. There's a machine learning researcher called Barak Perlmutter. He published it. Remember, we're talking about a function with an m-dimensional input that maps that gives a scalar output. So that function has a gradient, and if you send an argument into that function that is constructed like this, so x is the value that you're interested in. You want to evaluate the Hessian at x, but then you add some multiple of another vector to it. So alpha here is a scalar. So if we would just look at this vector here in the square brackets, if alpha would be 0, then that would just be the gradient. So we can calculate gradients with TensorFlow. So we've got the gradient. And so you can send x plus alpha y in the forward path and then get the gradient afterwards. Then if we would, do this calculation, of course we're going to implement this with a complex step trick in practice. But the mathematics looks like this. So you're making alpha infinitesimally small. So this is called a directed derivative. So if we're sitting at x and we're looking at the direction of y, how does the function change in that direction? So we can compute that using dual numbers. So you just send a dual number argument into the function. Afterwards, you get the derivative, and then the output, the real part of the output, is going to be the normal gradient, and the infinitesimal part is going to contain your Hessian vector product. So the equation here, I've written just one component of the gradient and the Hessian vector product, but in practice, it's one operation that will give you the whole gradient. So, and also in practice, you're not going to use a dual number. You're going to be using the complex step trick for this. So TensorFlow would not be equipped with dual numbers, but for most of the functions that you're interested in, it's going to be equipped with complex arithmetic. So you can just do the complex step trick here, and then you can calculate your Hessian vector product. So we've more or less done with forward mode automatic differentiation. So it's nice to theoretically define it in terms of dual numbers. It can be implemented exactly using operator overloading, but there's some coding effort involved there. Or you can very accurately approximate it using complex numbers, but there are some things to watch out for. Forward mode is no good to evaluate large gradients for optimization, but nevertheless, it's very useful for some other things. So maybe I should ask if there are any questions about this part before I go on. Ludwig. There's just one epsilon. So you need to, in practice, add the complex component to your input before you evaluate the forward function. So you can't evaluate the function at the real argument and then decide afterwards, oh yes, I want to do the Hessian vector trick. So you need to send the let's call it the augmented argument into the function at the beginning, and then do the back propagation. And because what happens when you call the forward function, if it's going to do back propagation, it effectively stores the Jacobian matrix somewhere, and then when it does back propagation, you multiply the vector that you send into the back propagation, that gets multiplied with the Jacobian transpose. But if you send in a complex argument, the Jacobian is going to be complex, and then that Jacobian times this vector y in which you're interested in is going to be complex. So that's the flow of how things work. Another question? The motivation is you don't have to derive the second order derivatives and code them by hand. That's the main motivation. So if you've already got your first order derivatives derived and coded, you don't have to do any more manual work to be able to get your Hessian. So for m variables, you're gonna do this trick m times, not m squared times, because you get a whole column out. So of course, the cost of getting that column is also proportional to m. So you're not going to do it for a large. You're not going to get the whole Hessian for a large Hessian. Right, you can. There are situations in which the Hessian is just diagonal. That often happens. So if you look at a neural net, and you regard this the part where you apply the nonlinearities as a mapping from a vector to a vector, then that Hessian is diagonal, and then it's much easier and simpler to work with. It depends on your function. So if for example you're doing logistic regression, so in logistic regression there's this matrix of weights, and if you want to optimize those weights, then you'll find papers where people have worked out by hand the Hessian matrix for that problem, and that Hessian has a nice structure. So yeah, you need to know things about the function that you're talking about, and then yes, there are many cases where there's a special structure, and then you can write code to evaluate the Hessian more quickly than in the general M by M case, sure. Okay, looks like everybody has a deep understanding of forward mode, and we can go to reverse mode. So, just to recap, so reverse mode is accurate and fast for computing gradients. Therefore, it's good for numerical optimization and maybe for a whole bunch of other machine learning problems. It can be implemented in a variety of ways, including domain-specific languages, operator overloading, or hand coding, if you like, some of which I'll summarize below. And it's available in several well-known toolkits, and of course, other toolkits built on top of these things, like Keras and Edward. They're also equipped with those capabilities because it's in these basic tools. So, reverse automatic differentiation computes gradients of function compositions by multiplying the Jacobian transposes in reverse order. So, the first thing you'll typically do is you'll evaluate the function just evaluate the function value, but if you know you're going to need to backpropagate, every little function block needs to store its own Jacobian matrix. So, some of those Jacobians are going to be huge. So if you would explicitly store that Jacobian matrix, that's going to require a lot of memory, but there are many cases where you don't need all that storage. So if you're looking at the bottom layer of a neural net, there's this big matrix multiplication happening, but the Jacobian is just the weight matrix itself, so you don't need to store it again. It's there already. The other example, which I just mentioned, that array of nonlinear activation functions, if you regard that as a vector-valued function, then the Jacobian is going to be diagonal, and so on. And if you, for example, differentiating through equation of a linear solution, if you're working with Gaussians, you're going to be doing that, then you'll find there's a rank 1 matrix that appears, and the rank 1 matrix you can store as just 2 vectors instead of the full Jacobian. So in practice, often you're not going to need to store the whole Jacobian, but implicitly what happens, forward evaluation, all the Jacobians are stored as you go along, and when you backpropagate, you're going to need to come back and multiply the backpropagating gradient with each of those rectangular Jacobians. So one way to implement reverse mode automatic differentiation is to use some domain-specific language. I think TensorFlow works like that. So the user defines his neural net or probabilistic model, whatever it is, in terms of some special language, and a parser then creates a computational graph out of this, for example, a directed acyclic graph. So the arrows point in the direction of the forward flow of the calculation. And then the DAG is converted to executable code, which will implement both the forward calculation of function value and the backpropagation. There's one thing to note about the DAG. So you'll get fan out in places and fan in places. So if you're backpropagating, wherever there was fan out, the same value gets used in multiple places. When you're backpropagating, you just add those. That's how the mathematics works out. So I've written code in Julia that does this. It was just an experiment, and it's not too difficult to do. A lot of work, but not too difficult. So you can also do on-the-fly evaluation of the DAG forward or backwards rather than code generation. And you can do optimization. Clever algorithms can look at the DAG and do stuff to make things run faster. So the other way to do it is with operator overloading once again. So in this case, you're going to specify your neural net or your model in terms of some existing language, some existing numerical language. And then you define a new non-numeric type, which can be sent as an argument into your differentiable function. So you need to overload once again the plus and the multiplication, all the scalar arithmetic functions, and your linear algebra and all the functions you will ever need. You need to overload them. And what happens when you send this special argument into your calculation, it actually runs the calculation in the order it would when doing the calculation, but it's just leaving a record of the calculation. So it's creating this DAG of how the calculation proceeded. If there's a loop, then it's going to basically open up the loop, and the DAG is going to have a node for every iteration inside the loop. I'm sure there are cleverer ways of doing it, but the brute force way of doing it is just like that. Also, it won't work for if statements because at the time when you send in that special argument, it's not going to look at numbers, so it's not going to know about which way to go in the if statement. So it has limitations. So anyway, once the DAG is available, you can do the same stuff you can do with the domain-specific language. So this works really nicely in Julia. I tried it in MATLAB and in Julia. MATLAB, I got some of the way, but some of the operators just couldn't be overloaded to work nicely. In Julia, it was really beautiful. But I'm not using it. I spent some effort at that. I'm not using it like that. So finally, you can just hand code your own automatic differentiation. So if you're working on a platform where automatic differentiation is not available, and you want to stay on that platform for some reason, you can hand code your own version of reverse mode automatic differentiation. So if you're going to be using matrices, linear algebra, then you're going to need to study matrix differential calculus a little bit. So I found this tutorial by Tom Minka very nice to give me a basic understanding. But there are other sources as well. There's a big textbook by Magnus and Neudecker. And many other resources. So if you want to do it by hand, you're going to have to study that a little bit. And then you would hand code small functional blocks. So the block would typically output the function value as well as a handle that can be used later for back propagation. Remember, you can't back propagate immediately. You've got to reach the end first and then back propagate through everything. So it gives you a handle, a function handle, and the Jacobian is effectively contained within that function handle. So then it's important to test every block using typically complex step forward mode automatic differentiation. And if the complex step fails for some reason, you can always fall back on finite differences. And once you've got the individual blocks working, then you can start hooking blocks together, function composition, and you test those compositions just to make sure nothing goes wrong. And once you've assembled the whole thing, you can still test it, because that's the stochastic test where you multiply the Jacobian from both sides with reverse mode and forward mode. That works. That's fast enough even for large architectures. So I've done this a lot. I like writing my own code. I haven't been using TensorFlow. And if you're doing unusual stuff that's not in TensorFlow, you can do that. So, in summary, about reverse mode, it gives you fast, accurate gradients. It's available in toolkits. It can be hand implemented if you like doing that kind of thing. Or maybe just provide a missing function in an existing toolkit. If I remember correctly, my ex-colleague Albert did that a few times, filled in stuff that wasn't available in, I think it was Theano then. Maybe a triangular matrix wasn't there in Theano, or Kolesky decomposition. And I mentioned this many times, test it, yeah. So, the final summary, automatic differentiation is not numeric or symbolic, so it does exactly what machine learning requires. It's fast and accurate. Forward and reverse modes have complementary capabilities, and they can be used to check the one against the other. And it's available in toolkits, but opportunities remain for some hand coding. And I can take some more questions.